Dana. I've never met you before, but I know a lot of people at Mongo. They do really cool stuff. All right, so my talk's called Learning to Learn. Try to get through it pretty quickly. So I know you guys are all itching to go hack, and I think something starts at 10. So quickly about myself, my name is Jason. I'm a lead programmer at Datadog. I actually write databases as well, so I guess you're only going to get kind of one viewpoint on software today, unfortunately, from people who started out trying to make video games and then ended up doing databases instead. I'm also an open source developer. I have a GitHub account that's pretty easy to find. One of the few fortunate things about having my last name is that it's always available online. So anything J Moiron out there, that's always going to be me. So yeah, let's get to it. So yeah, this is the first game that I ever played. I don't know if any of you recognize it. Probably do. Yeah, Legend of Zelda. It's the OG Legend of Zelda. So I have pretty much the same history as Dana, but maybe transposed forward in time, like maybe 15 years. This was the first game I played. I was quite young when I played it. I really loved it. You can like kind of walk around the world looks sort of like this. And I drew all my own maps, and I was like, if you've ever met the kid who's like, oh, wouldn't it be cool if there was a rock here, and you climb up here, and you find a spaceship and secret stuff. Telling lies to my friends about like all this stuff that I found that wasn't really in the game. That was me. I played tons of games, pretty much throughout my entire childhood. I didn't do anything serious with it, but I knew I really wanted to have some kind of future in video games, and I knew one of the things you could do to get there is to program. So I went to college, not really knowing how to program. I was actually quite handy at Smash Brothers though, so I'm looking forward to turning later. So I went to college, and this is kind of what I saw when I was looking at the code. I had no idea what was going on. I kind of struggled through my first year. This is why I said earlier, before I started, that I think a lot of you are probably way ahead of where I was. But I worked in some projects, like project courses with a couple other people. We kind of coded together, but a lot of times, like the really important parts, they were writing stuff down, and I was like, oh yeah, that looks good. That should work, but in reality, at some point, I had to like face the fact that I had no idea what I was doing, and this wasn't going to work. Like I was never going to be able to program video games if I didn't know how to program at all. So the summer after my freshman year in college, I was like, all right, I'm going to kind of sit down and we're going to figure this out. So I think the hardest project that we did freshman year, which was compressing a file, like writing a file compressor. Does anyone here know how these work? There's like a bunch of different ways to do this. So a super simple, like really basic version. So if you have files like this with really long series of kind of the same type of character, and this is actually kind of this kind of happens actually a lot in some kind of data. If you think of like a sensor, like some kind of sensor reporting a gauge, or like this is how much memory I have, like you can get the same value over and over and over for an idle computer. So does anyone have any idea of like how you could compress this? Yeah?
You would replace like BB with like another character, then just go through and replace it.
Yeah, that's one way. So that's like a general way. That's actually mostly how the compressor that I wrote was working. There's a sort of like super simple way to do things like this, which is like just count the number of characters and then like write out the number followed by the character that you're going to do. This is actually, it sounds like super simple and you can explain it in about 20 seconds. This is actually a real thing, a Wikipedia article called Red Length Encoding. I did it a kind of a different way, but I did something called Huffman encoding, which like counts the frequency of characters and then assigns the most frequent character like a smaller kind of bit length, and then you write out all the characters again with the new bit lengths. But essentially, what you're trying to do is you're trying to find some kind of repetitive stuff in a file. It's called entropy. Like non-random stuff is called entropy, and you replace some field that has a high frequency in the file with some kind of smaller token. You store the tokens and the values. This works really great on text. I don't know if any of you have seen this before. This is kind of an outdated version of how text works. Each character was one byte, it's 256 values in a byte. We only used the first 7 bits, so 100, 128 or 127 if you start from 0. Everything in the left column, there's only a couple characters there that actually make any sense in the text file, that actually result in some kind of thing. So like line feed and character return. And then there's some kind of principal characters in the other 2 columns. A lot of those don't appear in like normal prose. Like you're not often going to find a $sign or I don't know, some of the brackets and stuff. So really, you have 8 bits, but you're only using like 6 for most of your characters. So like right away, this works really great on text. Like I said, this is the old version, it's called ASCII. I'm sure a lot of computers still use this, unfortunately. ASCII is the American Standard Code for Information Exchange and Interchange, actually. And you can tell it's American because there's absolutely nothing there from other languages. So I was like, okay, I'm going to write my file compression. I wasn't a C++ programmer, I was actually a C programmer at the time. This is Hello World in C. A bunch of people here raised their hands when they said that they asked if we knew C++. So this is like pretty similar, kind of the OG version of C++. And I wrote this out. This was like, I knew this as like a thing. Okay, I write this out and then I can start writing my program. And I think you get this a lot in programming. Java, you have to like import some modules, and then you have to create a class, and then you do like public static void main. There's like a whole bunch of boilerplate in all these languages, and you're encouraged to just write this, and then you can start writing your program in here. And a lot of times, professors and tutorials and stuff, they'll gloss over what all that stuff means. But when I wrote this out, and I was like, I'm really going to learn programming now, I realized I didn't know what any of this stuff actually did. Like I was looking at this, I was like, okay, pound include, like, I know this imports some library, but how does it do it? When does it do it? Does it happen when I run my program? Does it happen when I compile it? This is actually, it's a whole Turing-complete macro language that's on top of C that actually essentially copies files into your file. So it's a kind of big mess. So like main, does it have to be called main? How does the computer know to call main? Like, how does the entry point kind of happen? How does the shell pass these arguments to this function? Like, what are the mechanisms by which this works? Printf, how is printf defined? Printf takes a variable number of arguments. You can continue to pass it a bunch of different arguments. And I had no idea how to define such functions. I had no idea how such functions could even be implemented. And return 0, like return it where the program is ending, and I didn't know what was going to happen there. So, yeah, I realized, okay, I really don't know anything about this. So I really dug in. Every time I looked at something, I asked myself, like, do I know this? Do I actually know what's going on here? And if I didn't, I tried to answer it, like, kind of to the best of my abilities. And this is kind of like the one big theme of this talk. A lot of people, you'll hear over and over again in your life, like people telling you about we've had this success, and you have to do this, and you have to do that, but no one tells you kind of how to get there. I think it's different for everyone. This is kind of how I did it. Just don't let yourself get away with thinking you know something when you don't. It's actually quite difficult to recognize when you don't know something. And it's a little bit scary to go around thinking, oh my God, I don't know anything. So like, how can you recognize when you don't know something? If you can ask yourself like really simple questions, like, what does this do, or how does this work, and you actually don't know the answer, then that means there's something more there to learn. There's like a gap in your knowledge that you can go and fill. If you know the answer, but you don't know kind of why that's the answer, or you don't know how you know it, or someone told it to you and you're just saying it, but you don't really know how they got there, then that's like, it represents another gap in your knowledge. And if you know an answer, but you can't test if it's correct, then you can't know it's correct, and that means that you don't know how to arrive at the answer in a verifiable way, and that's another gap. So I did this over and over. I eventually wrote my compression program, and I went back and I looked at the project that we handed in, and I read it, and I realized, oh, look, there's so much stuff in here that's bad and it doesn't work. And there's like lines of code that didn't do anything. They were there because they caused some other thing in some other place to function, but it was just by happenstance. I realized, oh, okay, not everyone is actually so far ahead of me as I thought they were. So yeah, whenever you find yourself in this situation, you need to go deeper. And there's a really great kind of classic interview question from Google, where they ask, what happens when you type google.com into a web browser and hit enter? There's a cool GitHub repo that had like a big collaboration from like electrical engineers and computers and computer scientists and network engineers and stuff that goes into really, really great detail, starting with like when the G key bottoms out, what happens in the electrical circuits in your keyboard and how that kind of goes to your, how that travels through your computer and kind of like how that interrupts fire in the operating system. It's like, it's a really, really long explanation. And it's about half the explanation before you even get to pressing enter and actually like using a network or displaying anything in software. Excuse me. So, yeah, there's a lot of simple questions that even professionals can't answer. Sometimes the answers to these are really complicated and people, it's actually like quite difficult to answer these questions. But in reality, like a lot of people just don't ask these questions, and it shows kind of the surface level of knowledge that you can have. So like, how does a file system work? Like how does it actually laid out on disk? How does networking work? A lot of people, they learn like OSI stack or TCP or something, but they don't know anything deeper than that. How do distributed systems recover from failure? Like how do you make a cluster of like 1,000 systems working together and then kill 10 and have everything kind of work fine and not really skip a beat? There's a lot of stuff that's like a whole discipline, and that's actually the kind of area that I did my master's degree in. How does an operating system boot? This is pretty deep rabbit hole. It's something that everyone does all the time whenever they turn on any kind of device, is that some kind of system boots up and initializes the device. But a lot of people don't even kind of know the basics of what goes on there. And how does the database store its data? So I know there's someone here that knows how that works, at least for some classic databases. But a lot of people don't really understand like what happens when you insert a record into a database, what happens when you insert a row into a database. And this actually has like real, the way that the database is working underneath actually has real consequences as to like what you can do with the database. So for instance, in a lot of like Square or like relational databases, you can add columns, but you can only add them if they can be null. Because if they can't be null, then it has to add something to every single row in the database, and then you have to rewrite your entire database. And a lot of databases are too big to do that. So, how are you doing on time? I know we have something. 30. We have something at 10.
Oh.
Can I go? Yeah? Okay, cool. All right, so I wanted to do the classic mistake of trying to do like a live coding demo. Also, I have a handheld mic, so this is going to be kind of interesting. But we're going to calculate the value of pi with programming. How many people have done Monte Carlo before? Okay, great, cool. So Monte Carlo is it describes like this class of algorithms that uses random sampling to estimate a value of something. The like 100% classic version of this is calculating the value of pi. So here we have a circle with radius 1. Oh, really So here we have a circle with a radius of 1. Does everyone know what the formula for drawing a circle is? Yeah, for graphing it, yeah. Yes, exactly. So here the radius is 1, so it's just x squared plus y squared equals 1. 1 is a really convenient value because when you square it and do a lot of stuff to it, it's a mathematical identity for a lot of things. So we'll stay with 1. So there's a couple things that we know about the circle. We know the radius is 1 because we drew it as 1. We also know its area. I'll try to just go through this quickly. So the area of circles pi r squared. And here, since we chose r of 1 because we're clever, that means that the area is just pi. So that's great. So how can we kind of figure out what pi actually is? It's famously irrational, so we can't really calculate it directly. There's like cool demonstrations of like unrolling a circle because pi is the ratio of the diameter to the circumference. But the Monte Carlo system, the Monte Carlo method to do this is you basically draw a bounding box around the circle, and we know that this is a square with sides of 2. So from -1 to +1 on each side. So we know the area that's is going to be 4. So now we have an area of pi and an area of 4 on the outside. And in fact, we can kind of simplify the maths a little bit and make it a little nicer for programming by only looking at the quarter circle and the unit square, like the positive quadrant. So now we have x and y coordinates of 0 to 1. And this is great because a lot of random number generators will generate that for us. And in fact, there's a lot of messy statistics with trying to take random numbers and then multiplying them or doing stuff with them and actually coming up with numbers that are still random. So all right, let's see. So let's try to write a little program here. So we'll just use Python. It's pretty simple. And can we see that? Oh, brilliant. We're on Linux as well. That's perfect. All right, so the first thing that we're going to need is a working keyboard. Okay, great. So we need random numbers. Let's just make sure that random numbers work. Yep, those look pretty random to me. Great. So we want to plot kind of random xy coordinates in our quadrant here, and we want to test whether or not they land in the circle or in the square. And if they land if we take the full amount of tests that we run, and we can use the hits. The ratio of the hits to the total number of tests, and then since it's not pi, it's pi over 4, we can multiply by 4, and we can get some kind of vector for pi. So let's first make a function that checks if something's in a circle. So we have the function that we use to draw the circle. So we can just check if x squared plus y squared is less than or equal to 1, then it should be inside the circle. And we can we know that like 1 is in the circle. We know that 1 should be in the circle. Oh no, 1 should not be in the circle, sorry, 0 should be in the circle. Okay, great, so unexpected, but that's actually exactly what's expected. And does anyone know sort of like intuitively if you draw a straight kind of 45-degree diagonal line up, what point you hit on the circle? Yeah, just the square root of, well, it's square root of 1/2. 0.5. Yeah. Yeah, it's the square root of 0.5 and square root of 5. So we can use that. We can do square roots as well. So, yeah, so we can check like a little bit more. So this should be okay. Yeah, that's in our circle. And then if we make it a little bit above, kind of on that same 45-degree line, then she gets it. All right, cool. So this probably works. In reality, of course, you would want to write like better tests, but this is good enough just for hacking. This is a hack day, so this is probably the extent to which you're going to want to be doing things, because you're going to want to move fast and fail early, as has been established. All right, so let's write our simulation. We'll run it n times, so we want to count our hits. All right, great. And we want to do, so for n times, we want to take two random numbers, we want to check to see if they're in the circle. If they're in the circle, we're going to increment hits, otherwise we're not going to bother. So, if in circle, that's in the circle. There we go. All right, it's fine. And then we're going to take the ratio of the hits over, to make it float. So does everyone know why I'm making it float? So that we get real number. We don't have integer division. So for instance, like in Python 3/2. Oh, this is Python 3. Oh, really? I didn't do that. Okay, great. So if we run our simulation with one random selection, we get pretty bad values for pi. That's not really anything like pi, is it? But it kind of makes intuitive sense. Like we're either going to land in the circle or we're going to land outside the circle. And we're going to say, oh, okay, it takes up the whole area, or it doesn't take up any of the area. But if we kind of start running the simulation at, scroll up here, with a little bit more, we start to get some better numbers, and we also, if we run it a couple times, we'll see that it's still kind of random. And if we can run it with, to do more and more, and then we see, we're starting to get something that actually looks quite like pi. I don't know how much I can abuse this website, but let's see. Okay. Yeah, great. All right, so that's it.